Okay, this video here is going to focus on the reaction that you see written up here, where we take an alcohol, a hydrohalous acid, hypohalic acid like HCl, HBr, or HI, but not HF, and in that transformation turns the alcohol into the alkyl halide and gives you water as a byproduct. All right, so this reaction, as I just said, is limited to HCl, HBr, and HI, but not HF. We're going to see that the reaction rate has a dependence on the concentration of the alcohol. But from this rate equation here, we're going to see that the HX does not enter into the reaction equation. Okay, and we're going to look at that in a second too. We have a relatively interesting effect here, and this is what we call the relative rate effect, that R equals tertiary is greater than secondary, is greater than primary, or methyl. The reaction is generally not efficient with primary halides, and we're going to, at the end of this chapter, look at alternative reagents to turn those alcohols into alkyl halides. All right, so what we're going to go through in the next few slides here is what we call a reaction mechanism for this reaction. It's a detailed description of the reaction, including all of the reactive intermediates and all the transition states. It's basically all the interesting things that happen between when we have just plain starting materials and when we have pure reactants. All right, so let's look at a few things about reaction dynamics here. Okay, and this is a classical potential energy diagram where we have on the y-axis increasing energy and on the x-axis progress of reaction. All right, so the energy is just going to be energy units like kilocalories or kilojoules or something like that, and as something gets higher up on this graph, it corresponds to it being higher in energy. It's hard to define the units of reaction progress. We'll just say percent completion is a good way to describe the units on the x-axis. All right, so here is a hypothetical reaction that's occurring in one step. Okay? All right, so here we have the reactants. Here we have the products. We say that this is an example of an endothermic reaction because products are higher in energy than reactants. Okay. But as the starting materials or reactants transform to products, the energy of the system just doesn't smoothly transform into the energy of the products. Okay? What happens here is that the reaction species that are partway between here actually are higher in energy than either the reactants or products. Okay, so you go through this curve here, and at the top of the curve we have something called the transition state, and this is the highest energy point along the reaction pathway. All right. The energy of activation is the difference in energy between the reactants and the transition state. Okay? All right, and the energy of activation has a very big effect on the rate of the reaction. This is the Arrhenius equation right here, where rate equals AE to the minus EA over RT. We're not really going to solve this reaction, this equation here. Just want you to know a few things about it. Okay, as the activation energy gets bigger, since it's a negative sign, that means the reaction is going to get slower. Okay, notice that this expression e to the minus e sub a over RT Well, this also tells us that as the temperature gets higher, it's in the denominator, I guess, here. So as this gets bigger, this term gets smaller and less negative. Therefore, the reaction is going to increase as we increase the temperature. Okay, reactions are, in theory, every reaction is reversible. So we have another value here, which I'll just call the energy of activation for the reverse reaction, and that is the energy of the transition state minus the energy of the products. All right, an important point here for the reaction that we're going to talk about is something called the Hammond postulate. The transition state looks more like the species that it's closer to in energy. All right, so this is an endothermic process, so the transition state here, we imagine, would look more like the products than like the reactants. If it was an exothermic reaction, the transition state would look more like the reactants. What you see here is a diagram for a one-step reaction. It has only a single transition state. Most of the reactions we deal with are going to be more complex than this. Some of them aren't, but we're going to use the term concerted to refer to a one-step reaction where we just see nothing interesting along the way, just a transition of products to reactants through a higher energy transition state. Okay, if we look at the mechanism for the reaction we're talking about, this is the generally accepted mechanism. I've used a tertiary alcohol, just simple T-butyl alcohol here as my example, because that is the one where the type of alcohol where the reaction occurs at the most rapid rate, and we'll talk about that a little bit later. Okay, all right, in step one, we are doing a general acid-base reaction. You can think of step one as being totally analogous to the Arrhenius equation, all right? And we know from the Arrhenius equation that a strong acid like HI, the reaction is going to the right. Thus, in step one, I showed a larger equilibrium arrow going to the right than to the left. Okay, so that's step one. In step two, we still have the iodine. I'm not showing it in step two, but let's just remember that the I- is still present. It's just an innocent bystander in step two. But in step two, we are losing water to make a positively charged carbon, and this is an important type of what we call a reactive intermediate in organic chemistry, and this is evolving water as a byproduct. This is actually the step where we form one of the products of the reaction, water. Okay, so carbocation is a reactive intermediate. They typically are not stable. They exist only as part of a mechanism. Okay, so they're an intermediate in a reaction, but it's really hard to isolate them. There are very few examples of stable carbocations. We will see some toward the end of Chem 313. All right, in step three, what's happening here is that our carbocation is reacting with the I- that was a bystander in step one. Remember, it was actually generated in step one. It's a bystander in step two. So the I- is reacting with the carbocation, and this makes the final product. All right, so I explained why I gave the first step a forward direction arrow. Let's look at step two. Why am I giving it a reverse direction arrow? All right, so if we think about the structures of these intermediates here, this looks to be something that's not all that favorable, right? And this is because we have all octets here for every carbon and oxygen in that molecule, whereas the carbocation really only has 6 electrons at carbon, so it and has no octet. All right, okay, so we have that. For that reason, we're going to designate this reaction as endothermic. And all the bad things we said about step 2 are undone in step 3. This is where we take the only thing that doesn't have an octet, the carbocation, and we give it one by reacting it with the I- in the solution. Okay, all right, so here's a little bit more. Okay, one other issue here. Why does HF not work? HF doesn't work because of its effect on step 1. HF is not a strong acid, so with HF, step 1, the reaction goes to the left instead of to the right, and because of the failure to generate a high concentration of the step 1 product, we do not see a successful reaction with HF. Okay, so here's just a review of what we said here. Step 1 is exothermic and fast. It can be inferred as just an analog of the Bronsted-Lowry equation, substituting an alcohol for water. Okay, and this step should be regarded as very fast in a pre-equilibrium. Okay, step 3, this is the one where we got rid of the octet. That's also very fast and very exothermic. The only species that doesn't have an octet, in this case, the carbocation, acquires one. This step also really eliminates all of the charged species, so it gets rid of all the charges as well. All right, in step 2, this is the slow step of reaction, and it's also the least favorable. The overall rate of a reaction is affected only by its slowest step, and this is known as the rate determining step. We're going to give it the abbreviation RDS. Okay, our chemical intuition is basically telling us that the step shouldn't be all that favorable, right? Since there is, it's the only species where we generate the compound that lacks a full electronic configuration. Okay, the rate effects noted a few slides ago where we said R equals tertiary greater than secondary greater than primary greater than methyl are all due to how these groups affect the rate determining step. All right, as we stated early on, the rate is a function of only the alcohol or protonated alcohol. Iodine does not enter into the reaction equation. We can look back here and see that in the slow step, we've given iodine a role as an innocent bystander. It has no role in the changes that occur in step 2. Okay, so it's not part of the rate equation. The rate, as we're going to see, is going to depend on how easy it is to form the carbocation. We're going to see that alkyl groups are going to be stabilizing to carbocations, and this is going to account for the higher reactivity of tertiary alcohols. All right, so here's a potential energy diagram for this reaction. Remember, we said that it had 3 steps, and here you see 3 distinct transition states, right? So we see transition state for 1 right there, transition state for step 2 there, and transition state for step 3 there. All right, if we look at each step individually, we're going to look at how the rate is dependent on the energy of activation, which, remember, is the energy of the transition state minus the energy of the products. Okay, so the energy of activation 1 is a relatively small number, energy of activation number 2 is the largest of the energies of activations in this reaction pathway, and the energy of activation of step 3 is also quite small. All right, okay, so let's look at step 2. Step 2 is our slow step of the reaction. Remember the Hammond postulate. The transition state's going to resemble the species that it's closest to in energy. All right, so in step 2, it's a very endothermic reaction, so the transition state is much closer in energy to here, the carbocation, than it is to the protonated alcohol. Thus, we can say that all the effects of the rate that we're going to see are due to how the structure of the molecule affects step 2 of the reaction. And we can attribute it all to carbocation stability. Okay? So I believe that this is where I'm going to stop this video here. The next thing we're going to talk about is how alkyl groups affect the stability of carbocations and how that affects this reaction rate. Okay.